Okay,
Right.
seem to have it. Okay, so talking about capacitors, and actually, I was wanting to. I'm going to unshare for a minute here if I can find the button, because I wanted to just show around the room a little bit. Well, I'll do that afterwards. Anyway, capacitors store electric charge. If I can find the, I got my, there, I got my laser pointer on. Yeah, you might think of this as a unit of charge. You know, after you've been working out in the yard, with a lawnmower, that unit of charge can sometimes help you a bit. But yeah, it actually has some resemblance to the Leyden jar, which was the original capacitor. Uh, Originally, they actually put liquid inside it because they thought the charge was held in the liquid. Ben Franklin was actually the one that discovered the charge was held in the glass itself rather than the liquid. But you can see the bar up there. So actually, I could have taken that, pulled the cap off, and put a rod down there with a ball on top of it, and used the uh, thing of Corona as a Leyden jar for whatever that's worth. Okay. Okay, a capacitor, we've got a dielectric or an insulator, the glass in the Leyden jar, a metal plate and a metal plate, and some kind of connections to it, and variations of this construction here. Uh, it's basically, well, we got a schematic symbol that we commonly see for it. Yeah, regular capacitor, an electrolytic, and variable capacitors. You got to remember it's a storage unit for electric charge, and that charge is basically an accumulation of current in the capacitor. Got the seahorse there because integral sign is sometimes seen as a kind of an intimidating thing to people. But seahorse looks a little friendlier there, so I've decided integral signs are really a seahorse. I guess two seahorses would be, a two pair making a family, and three seahorses. Well, let's not talk about that, but everybody's had to solve a triple integral would know about that. But anyway, voltage on a capacitor is integral, which is basically just summing up the result of current over time going into the capacitor. You can see down here, I've got my bucket of water and a faucet flowing into it, which is essentially the same thing there. You can see the, oops, did I get that? There we go. So we can see the water flowing in and the water accumulates in the bucket. Basically the same thing. Instead of electrons, it's water. We're filling up a bucket, a container, a capacitor, and on there. Now, lots of times for work, like I've done a lot of work in switching power supplies, and it's more common to use this form, which is basically a little scribbling from calculus class, and you can get from this form to this form of the capacitor, and generally more useful. And then there's another form that we use that commonly, which is the X of C, which we're looking at as an impedance. So you can more or less use sort of an Ohm's law type of rules with capacitors. And that's derived from that above. And there's a whole lot of calculus to get from this to this. And it's, it's a pretty nasty calculation. But this is much easier to use for somebody who's working anything frequency domain, like solving RF filters on a switching power supply is a common use of it. And by the way, there's actually a J in front of this here to tell you that it's a 90-degree phase shift of the impedance, that it's not just like a resistor. But for a first shot look at things, lots of times that's all you need. And that's what they normally put in like radio amateur's handbook or technician's literature. Another way to look at the capacitor is you put the capacitor with a resistor, and you have the capacitor will charge to the resistor and from a voltage source. And as the capacitor charges up, the current through the resistor drops so that it turns into an exponential function there. And that's lots of times used for timers that 0.694 times the value of the resistor times the value of capacitor will tell you how long it takes to get to 50% charge, which is used in a lot of circuits. Or if one RC time constant, it'll get to 63 point something percent there. 63 is a good number for a first shot at it. So that's lots of times used in timing circuits, timing circuits, filter circuits, and things like switching power supplies and integrators and things you get to that. What's our capacitor good for? In some cases, it's kind of a measuring cup for charge. I mean, there I'm, getting ready to make pancakes one Saturday morning there, and pouring the, soy milk, which we have to use because we're allergic to cow's milk. But anyway, pouring that into a thing, and we're going to carefully measure it. And so, measuring cup with charge, again, we'd have places where it'd be used in integrator, timing circuits, filters, resonant circuits, A to D converters. Those things, you're making an accurate measurement. So you need a capacitor that's quite accurate. Other cases are more energy storage, like power supply filters and bypass capacitors, coupling capacitors. Those are much less critical. It's kind of like the mixing bowl. The exact size doesn't matter as long as it's big enough to hold all your ingredients when you pour them in there. You're good to go with that. So here we're going to compare our measuring cup to a capacitor. In this case, I've got actually a kind of antique polycarbonate capacitor, which is a very high quality part for accuracy. But anyway, measuring cup, we want it to be a pretty exact size. A capacitor, we want a pretty exact value. You need a rigid shape for the glass here, so when you pour liquid in it, it doesn't stretch. Capacitor, you want one that it doesn't change with voltage. You really wouldn't see temperature effects on a measuring cup normally, but still, it's something made out of Pyrex glass. It's going to be stable with size. Same with the capacitor. A good capacitor is stable. If you had a measuring cup with porous sides, you'd get some of the liquid go into it, and you wouldn't get it out right away. And that would be like dielectric absorption in a capacitor. I'll talk a little more about that later. And no leaks. If you had even a pinhole leak in here, throw off your measurement. Same with the capacitor. You want something no charge leaks out. In other words, it should be pretty well perfect insulator. Now here we're going to look at just a storage container or mixing bowl capacitor. I've got here a picture of a electrolytic capacitor, which are normally used in power supplies for energy storage. And the value is pretty sloppy on those. I mean, some of the cheaper ones are marked -20 plus 80% on tolerance. In other words, they can be 80% higher than marked and still shipped as a good part. And again, like the mixing bowl, the size isn't critical if it's a little bit big. If it's too small, you definitely have a problem when your mixing bowl will overflow. And if your capacitor is too small, you have problems with a unstable power supply. The sides, you could mix in a soft plastic bowl with stretchy sides, wouldn't really hurt anything. Again, the electrolytic capacitor, change the capacitance with voltage. Well, we're just storing amount of charge. It doesn't matter. Little leakage would be okay. Actually, on the mixing bowl, you probably wouldn't tolerate any leakage because make a mess of your kitchen. Take a look at another thing in a water system for a house. I like to have analogies with something you can put your hands on. Electrons, you can't see them. You can only see their effect with instruments, whereas water, you can see it, feel it. So my house on a well pump, so you got a tank there, and the pump cycles on and off. It'll bring the pressure up to 50 pounds in the tank there, and then it'll go down to 30. But the pump itself, the pressure coming out of it is either 0 or full steam, and the tank is leveling it out, just like a big capacitor in a power supply will level that out. There's another thing. Okay, so that's for slower changes. Now, sometimes you've seen the thing where you suddenly turn off a faucet, or, washing machine valve changes and the pipes rattle, that kind of thing. And they put these hammer arresters on there, which are basically something, they have an air cushion in there, and it allows it to store up a little bit, and it reduce the impact of that. And on digital logic chips, you have the same problem, really, that you have chips pull currents in big crazy spikes, and you need capacitors very close to the chip to handle it, just like these things need to be close to the washing machine to stop the shaking pipes. So there'll be little bitty ceramic capacitors, either that or little chip capacitors, but they're right close. Take a look at ceramic capacitors here. There's two different flavors of ceramics that seem to float around, or basic flavors. There's a class 1 ceramics, which are very stable. They're using filters, timing circuits, somewhere you want to actually have a precise capacitance value. They have a whole bunch of flavors. The C0G is the only one that you normally see in engineering, unless it's something very specialized. Then you might see some other stuff. ceramic capacitors will look like this. And you can't tell a class 1 from a class 2 from looking at it, other than the case size gives you a clue that these are quite large and bulky for a given amount of capacitance. Class 2 are very small. However, they're not very stable in capacitance value, and they're microphonic. And they're also speakers that if you hook one to a signal generator and drive big spikes into it, you can actually hear it singing. Or if you bang one while it's hooked to a scope, you can actually see it puts out voltage pulses from mechanical force. So got a lot of bad behavior, but it works perfectly well for the thing of power supply filtering on logic chips. I mean, all the hundreds of logic chips we have in everything, those capacitors right near the chip are very critical, and they're almost all class 2 ceramics. They got to need to be small, cheap, and and do the job, which they do. There they've got several ratings, X5R and X7R. If you're going to a catalog buying a capacitor like DigiKey or Mauser, one of those suppliers, those will be basically stable over temperature, won't wander around much. There's Z5U, which they'll try to sell you. It's cheaper. It's only usable for indoor applications. Then you see Wi-Fi-V, which I never put either of these two in designs. I always put these because they cost only slightly more, and most of the equipment I designed over the years had to go in outdoor environments. They look at the temperature coefficient of those capacitors. So what happens when you move the temperature around? Now imagine we're putting this capacitor on some logic chips or some things that out at the dish feed, some electronics out there. There's lots of times you turn up with electronics at the dish feed, it gets exposed to temperature extremes. If you put X7R or X5R capacitors, the same curve, only doesn't go quite as far on the high temperature end. You can see everything would behave fine over minus 55 to 85 degrees C, or X7R all the way to 125 degrees C. So any temperature you're likely to expose it to, the capacitor just sits there and does what it does. Not a super capacitor, but it's very stable, relatively stable over temperature. The Z5U, you can see if you put it in an indoor application where you might see 50 degrees C, maybe 20 to 50. It's reasonably close and likely to work. Wi-Fi-V, put that capacitor in there, your equipment heats up, the capacitance drops, and you don't have enough capacitance on your logic chips, and they start doing crazy things, or op amps, they start oscillating. All those things need a minimum capacitance to behave. So if you're buying capacitors at any project, even if somebody specifies one of these others, just get an X7R. You'll be happy that you did it if you expose it to any temperature. Okay, and then what's the dielectric material? Oops, I grabbed the wrong thing there. There we go. So we have the polyester film capacitors. They're made out of a plastic, just like polyester, and for clothing and stuff like that. Same thing, polypropylene. You see those in a lot of normal day-to-day applications. Polyester, it has a good electrical characteristic, small size, and cheap, generally good. If you have a need for a really precision capacitor in larger values than you want to go with ceramic, polypropylene is good. It's a little bigger than the polyester, but its electricals are super good. And these look the same as those. It used to be years ago that the makers of polypropylene in these little boxes always used green plastic, but about a little after 2000, they stopped doing that, started using all different color plastics. I kind of like the color coding of green was polypropylene, but they did away with that. These do cost more. And then, of course, most modern electronics is surface mount assembled by robots. And there we have the PEN capacitor. It's PEN because nobody other than a chemist can pronounce the name of it, so that abbreviation is used. And that's similar to a polyester, except it's a surface mountable part. It's made out of a plastic that you can expose to extreme soldering heats, and it doesn't fall apart and change value. And then they've got the PPS, which is similar to polypropylene, but it again will withstand all the abuse of the soldering process. And it's a super good capacitor for applications like timing or filters, whatever. Then we have the electrolytic capacitors. They get a very large amount of capacitance in a small space, so they've got a value associated with them there. So you get a small size. It's interesting, the on the electrolytic, aluminum oxide is actually the dielectric, and they're made by, you take two pieces of aluminum foil and you put paper soaked in a magic chemical goo, which is secret formulas, but anyway, in between those two, bring wires off the two foils, you wrap it up in a jelly roll and put it in a can, and you don't seal the can because this electrolyte material is superconductive. So it's got a conductive path between the two aluminum plates, or it's shorted when it's first manufactured. And then they run a current through it, which causes aluminum oxide to form on one of the plates. And they keep doing it at higher and higher voltages until you get to somewhat, if it's a 50-volt capacitor, they may do the final forming at like 75 volts or so. And then after that, they get, a capacitor will always work reliably at 50 volts. The aluminum oxide is that thick. So it's small size, large capacitance. The electrical characteristics are pretty poor, but hey, good enough for an energy reservoir and a power supply, which is what they're used for. Then you have a tantalum dielectric, or tantalum capacitor. Tantalum oxide is a dielectric. They're made by, kind of like the electrolytics, but the electrolyte material is solid. They're more stable and they have very little leakage current. So they're sometimes used in timing circuits where you need a bigger capacitor and you get a couple hundred microfarads of those. And then we got various variable capacitors show along, which we'll go over. You got the air variables where the air between these plates as they're moved is the dielectric. And then you got ceramic. There's a little ceramic disc rotates over a metal plate underneath, and you got them made out of plastic film. Then there's the piston air capacitors, which are interesting. These first three, they're usable to maybe 400, 300 or 400 megahertz. They still behave reasonably well. These are very low loss and will work to a couple of gigahertz. So they're lots of times used in the past in preamps. More modern preamps are lower impedances and don't need those so much. Then there's another capacitor floating around, the porcelain capacitor. It looks like a ceramic in construction. However, porcelain is very, very low on losses. And a little capacitor, 1/10 of an inch long, can have kilowatts of power going through it and not explode or melt down. And because of the low loss, they're lots of times used in preamps now, where we used to use the piston trimmers. They put, fixed capacitors because the FETs for preamps have much better control now. But the porcelain, I said they're almost lossless, and any other capacitor you'd add to the noise figure of your preamp, not a good thing. Take a look at an equivalent circuit of a capacitor. You got your basic capacitor, what's marked on the case. Then you got a resistor inside in parallel with it, and all these other components are undesired things. You have some series resistance there, and then because of the structure of it mostly, you have some inductance there, and these things can be headaches sometimes. And then we have dielectric absorption, which is an interesting thing. You have a capacitor, let's say 10% dielectric absorption. This capacitor, which is kind of a phantom, would be 10% of the value of that one, but it's got a very high resistance in between. So if you charge a capacitor up to a high voltage, the problem in like radar power supplies, you can have 5,000 volts sitting on an oil-filled capacitor. You think it's discharged, you let it sit a while, and this capacitor held some charge, discharges in this one, and all of a sudden that capacitor was sitting there, you thought it was discharged, has 500 volts in it. So it's mainly in high voltage places or precision measurements are the two things where dielectric absorption gets you, because you don't want the capacitor to misbehave in any way. Let's go to series inductance, because that's the thing probably the most interesting to us. And this would be like for a typical chip capacitor. You have 0.8 of a nanohenry, very small amount of capacitance. But that will form a resonant circuit with the capacitor and cause it to, above a certain frequency, the capacitor ceases to look like a capacitor and becomes an inductor. This is from some of Howard Johnson's work. You notice this one's 20 years old and still applicable. You just move the things around a little bit. But a capacitor will have a range where it bypasses noise on a logic chip, and beyond that it won't. But the inductance is lots of times a headache in a capacitor. Here we got a little disconnect with reality here that happens. You mount a capacitor to a circuit board, and the capacitor, when it's mounting, would have this this area here, because capacitor or inductance is associated with a area enclosing a magnetic field. So we got this area here enclosing the magnetic field, except when we mount it to the board, the whole path to the IC we're bypassing goes like this and this. So all of this area adds to the inductance, and we don't have adequate bypassing at the capacitor at the IC because there's too much inductance there. So that's critical in logic chips, among other things. This capacitor would in fact be mounted in a different manner so that it's much closer to the IC chip, because the chips can misbehave. Memory chips forget things, and flip-flops flip the wrong way, and other bizarre stuff due to the capacitors not being good enough. So the proper mounting of the capacitor next to IC chips is possible. That also gets into the area of radio frequency interference. Every digital logic chip is a radio noise generator, sometimes a pretty strong one. As a matter of fact, DRAM chips are among the worst because they're clocked at a constant speed, and it can run you kind of crazy. But the mounting of the capacitors is very critical in something like that. And it's mainly because of the undesired inductance that you accidentally made in your mounting method. Now we're going to go to the feed-through capacitor, which is of some special interest there to us, as we'll see in a minute. Feed-through, you've got you can see the construction of it. There's a bar there, and the capacitance is between that bar going through it and the outer housing. This one's mounted with a threaded nut. This one would be soldered into a wall. This is a surface mount one, which works nowhere near as good because it's not going through a wall. But because of its construction, the stray inductance sitting here can be very, very small, and it results in the capacitor being free of resonant effects on this part of it, all the way out to 10, 15 gigahertz lots of times with a well-constructed capacitor. This may sound kind of academic until the next slide here, but anyway, we've also got the inductance related to these bars here, which is somewhat larger, but that's in series. This is the point we're trying to keep signal from getting from here to here, so series inductance doesn't hurt us really, but we need the very good path here. Then the feed-through capacitor is mounted in the wall of the box, and soldered or bolted in. So that box leaves a protected area. And if the feed-through is properly installed, radio signals, noise, whatever out here is effectively bypassed to ground by the capacitor going through the wall of the box. So you have a protected area here. The feed-through capacitor becomes part of something here. In my IBT, I built my own sort of satellite finder thing. Got one of the boards with the little logarithmic detectors made for cell phone, cell site signal leveling control. And they're very accurate little chips, and they do make a pretty good thing for your IBT. However, I initially just had the thing mounted on the chassis there and thought that was good, connectors going in and whatever. This wideband chip would pick up Wi-Fi signals, cell phone signals, alarm system signals, all kinds of things there. As soon as I put it inside of a metal box and then put the feed-through capacitors on all lines through, it would work great once I sealed the lid of the box. Until the lid of the box is sealed, the feed-through is not doing any good because signals can go around the edge of the box. But once a box is properly sealed and signals brought through with feed-through capacitors, higher frequency stuff is very effectively removed. Now for lower frequency stuff, sometimes a larger conventional capacitor will be hung like from the pin of the capacitor to ground on either the inside or outside, because you do have a limited amount of capacitance here. So for low frequency, but for all the high frequency stuff that was running me nuts, those 3 feed-throughs on the control lines and output line going in there, all of a sudden left it so no problem at all with interference. The laptop can run next to it. The Wi-Fi doesn't talk in here, and a bunch of stuff like that. Then there's the extreme case. I don't know if they're doing any of this at NRAO, but I spent some time in the Air Force working on comm nav equipment. and you found that wherever the control signals from the control box went inside of something, you always found there was a double wall box there. You went through a feed-through capacitor, and then there was a small inductor put inside there, and then a second feed-through capacitor. And this was made because you need extreme isolation for military stuff. There's also something that they called Tempest, which I was only briefly exposed to, but it's basically you don't want any of the operational signals inside a box finding their way to the outside world and being detectable at all on the wires by anybody spying or whatever. So this combination here gets used a lot by the military for the extreme isolation. You have a radar transmitter and a very sensitive receiver right next to each other on a plane or a ship. Without the double wall box and the super thing, it just doesn't work. I have yet to see a place where radio telescopes have actually used that, but with as noisy as computers are getting, we may get there where we have to double wall going inside of our RF equipment boxes. Let's take a little look at a DC power line filtering application. In this case, laptop computer dies, the screen gets crushed and it's old enough it's not worth. You got this 19-volt power supply laying around, which is made for the laptop computer. It puts out a reasonably good 19 volts. However you start looking at it, there's a lot of noise on it. Everything in the world uses switching power supplies, and switching power supplies tend to make noise from DC up to blue light. Well, this thing has plenty of watts out to run things like my IBT and other such stuff. The only thing is it's noisy as heck. So I ended up putting a filter network there where capacitors and ferrites were the big part of it. So in this case, I'm going to kind of go through each component. We've got L1, it's what is called a common mode. So any noise where both these lines are trying to move together with the noise is filtered off by that. And I put a ferrite sleeve on there, which is good over very good at very high frequency range out to 1,000 megahertz. Below 20 megahertz, it kind of falls aside. Then for differential mode, put a couple of small ferrites there. And then 100 microfarad electrolytic capacitor, the normally evil guy if you're looking at accuracy or whatever. But here's exactly what they made for. They hold a lot of energy. They level things out and keep care of all of the noise up to about 5 megahertz or so. Above 5 megahertz, the little ceramic caps take it. And you have each side of a choke coil, and the choke coil combination. Now this choke coil would be for the lower frequency noise. So by the time you've went through all of this stuff, you've got a pretty clean power supply here. And then I went through a 12 and a 15 volt regulator because I use both voltages in the IBT because that's how you switch polarization. The 7812 regulator calls for 0.1 capacitors, microfarad on it. The 0.1 microfarad capacitors are put there to make the regulator stable. So those aren't put back here. They're put immediately next to the regulator with the shortest wires possible to ensure the regulator behaves itself. So those want to be within a couple tenths of an inch of the regulator pins to make sure the regulator behaves. Regulators are pretty clean outputs generally and don't need a lot of output capacitance in most applications. By the way, part numbers I put in there, and this is in my paper, the same thing, came from DigiKey. And I just use them because their online catalog for selecting parts, works pretty well for me. Mauser Electronics also has a similar thing. I'm less familiar with their catalog. Others out there, the catalog thing isn't as good, so I'll always use one of those too. And then we're going to look at logic ICs. What happens? You got a board full of logic ICs. I mean, this is interesting to the guy that designed the Raspberry Pi or the Arduino boards, and sometimes they weren't interested enough because those boards generally put out a little bit more RF noise than necessary because they didn't do the best job of putting the little capacitors right next to the chips. And with the modern higher speed chips, you actually turn up with a very small capacitor next to each logic chip right at the power pins. And some larger logic chips may have 4 or 5 capacitors, sprinkled around them to get the desired effect there. of keeping it, the chips working reliably. Like I said, logic chips, registers lose their mind, memory forgets stuff, other such things if the power lines aren't stable. So you'll have 5, 3.3, and cores of some microprocessors are getting down on 1.2 volt or whatever for the inner core. But whatever, the bypass capacitor is critical. Now these will always be ceramics, normally X7Rs, that's where they're applicable. But you'll almost always have a tantalum capacitor on the board somewhere. And tantalum is interesting because they have some series resistance inside of them that's fairly consistent from part to part. And that series resistance actually damps out the oscillations you get because you got a capacitor here, inductance of your power feed traces working together, and you can get a little ringing from that, and that damps out the ringing. So if you replace that with a super quality capacitor with no series resistance, your ringing would build up and you may get an unstable supply. Yeah, this is kind of power supply from past history, so it's probably not too applicable. But an interesting problem I ran into once, gave a design to a draftsman to lay out a circuit board, and the ground point for the regulator was tied right here at the rectifier diodes rather than right at the filter cap. And the result of that was as the pulses from the power line charge the filter cap, you get a voltage drop across here. And this voltage drop would move the ground pin for the regulator, which tells it what it's supposed to regulate its output to. So you turn up with this noise on the output of the regulator, which was actually a couple hundred millivolts due to the poor layout. And all I had to do was cut the filter cap trace from there and put it where it was common with everything else, and things suddenly work. So for a capacitor to work right, it needs to have good connection to the points that it needs to filter. It can be quite important. Yeah, not much else to say there because nobody's building power supplies anymore in general. Now this is a case from a radio receiver that I'm still using, which is an analog receiver, and I'm using a polypropylene capacitor and a resistor to make the integrator stage, or essentially low pass filter for my data from my detector. This capacitor, I've actually got several of them. They can be switched in out with some little switches as needed. But they're a polypropylene capacitor. Actually, I used a polycarbonate, excuse me. But polypropylene is what you would use now because they quit making polycarbonate. The one factory in Germany that was making polycarbonate film quit, so all suppliers of polycarbonate capacitors went away. Polyester might work fair there, but the polypropylene is much, or polycarbonate are both much better because they don't change value, don't have any dielectric absorption. They're just a pure capacitor. So when you integrate something, the result is pretty pure. If you use a tantalum capacitor there, it'd do pretty bad. An electrolytic, it'd be an absolute joke. A high K ceramic, class 2 ceramic there, be microphonic, vibration from your fan would add to your radio telescope data, for instance. Now, one thing that's interesting that when you get a large capacitance going into a, IC amplifier like that, if you turn the power supply off and the power supply dies quickly, the energy in this capacitor is going to try to go back to the IC and, in fact, blow it out. The experience speaks. So you have to put a small resistor in series there just so the current available in the capacitor can't get large enough to blow the IC. So that's something I learned from bad experience. You really need a resistor there from that. Most of the time, of course, the integrator function is moved to software in a modern receiver. Okay, most people are just buying little preamp things, but in the past we used to make our own, gas FET preamps and or hemp FETs or the various type of FETs. But the capacitor selection was very critical. The source leads, sometimes some designs actually depend upon having a slight inductance there, so you have to use the same capacitors that the original designer of the preamp used. This capacitor is not too critical. This one needs to make sure there's no RF there. Small resistor to your really big capacitor there. These two capacitors are critical because any loss in them adds to the noise figure your preamp. You bought a very expensive FET. Well, now they're $1. They used to be 40 bucks for a good FET. And after paying 40 bucks for a good FET, you don't want to sacrifice any noise figures. So these capacitors and the inductor here also were selected very carefully to have almost no loss. So that's where things like the porcelain capacitors and the inner piston trimmers came in. Then there's the stray cat and the stray capacitance. Everybody's seen a stray cat show up occasionally, don't feed it or it's your cat after that point. But anyway, stray capacitance, it also shows up. You turn up with a capacitance, you wire insulation, it's an insulator, it's a dielectric, inside you have copper. So you turn up with capacitance between these wires. And I've seen some real disasters happen from cables. Somebody puts a line to power a compact fluorescent display, the backlight on it, along with a some logic signals and other power signals, and there was all kinds of garbage coming across. It was all due to the stray capacitance between the wires. Somebody just forgot there was capacitance there. Sometimes there's a thing called the ribbon cable where the wires are glued together in a specific order or make a little ribbon. On those, you can control stray capacitance a lot better because in your ribbon, you hook every other conductor to your circuit ground, and that can leave you quite good isolation going down a cable. Not quite as good as a shielded cable, but pretty good. And how am I doing for time? Okay. Oops, back up one. Talk about electrolytic capacitor failures. Electrolytics are something that there's some definite ratings on them, and manufacturers of PC motherboards and PC power supplies have not been good about keeping the ratings proper. You can see that capacitor's bulging at the top. This one's got chemicals leaking out. This one's got a bulge, lifted off the board, stuff like that. And more extreme cases, a capacitor goes boom, sounds like a firecracker going off inside your computer or whatever, and there's confetti all over the place with a nasty smelling chemical associated with it. In applying electrolytics, something called ripple current and ESR has to be watched. Fortunately, nobody designed switching power supplies except people that really get into it. You buy a switching power supply and hopefully they did a proper job on selecting that. And of course, I've got my crazy conspiracy theory. When they make the power supplies and the computer motherboards, they purposely undersize the capacitors so that they'll have a slow failure. If you undersize semiconductors, they normally die pretty quick. But you undersize electrolytics, they just kind of gradually get worse and worse. And after 2 years, right after the warranties went out, the capacitors got bad enough that your power supply, had a capacitor go boom or it quit. Electrolytics aren't working right on your motherboard, and the power supply becomes unstable, and the computer starts doing wacko things because the chip's not following its instructions properly. So anyway, little conspiracy theory. It's really the manufacturers trying to assure they wear out in the proper time. Who knows if that's true or not? Maybe it's just trying to make the design as cheap as possible. But anyway, if you ever look at your PC motherboard and see capacitors bulging, it's time to replace it. They're going to go. Same with power supplies. They go, I first got on the thing with power supplies when I was designing a power supply for LED lighting. And the power supply for LED lighting was a big bulky thing. And the salespeople said, why is that thing only 140 watts? It's twice as big as a PC power supply that's 400 watts, And I had to explain, well, I took a few PC power supplies apart that had died and showed them, well, we don't want this happening to our lighting power supply because we claim it's going to last 10 years with virtually no fallout, almost no failures in 10 years was our goal. Versus a PC manufacturer maybe wants it to die at 2 years. I don't know. Our power supply for lighting would go up in an attic, so the outside temperature might be high, no cooling fan, so it'd get pretty hot. So, that was when I started looking at, well, what do they do in PC power supplies? And I found out that I was not impressed with their rating on capacitors, because I reverse engineered a few designs and I'd say, well, I'd never do that. Of course, I'm designing industrial equipment and they're designing for a mass consumer market, a little different of a game. Anyway, oops, back up one. There's a picture of me at work in my lab there. See, I've got my capacitor on a capacitance meter, a little candle and all that. Little silliness. And time for questions there.
Well, we got one from Don. You're going to talk about a variac capacitor.
Oh, okay. I put it in the paper about the varicaps, which they're a semiconductor junction always have some capacitance, and for electronic tuned oscillators, because almost all receivers now, the oscillator is actually a electronically tunable oscillator, and a bunch of digital circuitry measures the frequency and tunes it to a very precise frequency. And so that you're taking advantage of the capacitance of a semiconductor junction. As the voltage goes up, the depletion layer in the semiconductor, the area where there's no charge carriers, becomes larger and larger on a reverse bias semiconductor. So as that distance becomes larger, the capacitance drops. So if they optimize the mix when they're doing the magic of making semiconductor devices to for the capacitance, they can turn up with a capacitor that's reasonably low loss, and they can electronically tune it over a range of maybe 3 or 4 to 1 on capacitance, and still have pretty good behavior. So that's how phase. Anytime you see something with a phase lock loop, they had a varicap or a voltage variable capacitor, which was actually made with a semiconductor there for that. The other place where variable capacitance of semiconductor junctions has been used is in high power frequency multipliers, and that's falling by the wayside because they've got transistors and things that work at those frequencies. But originally, if you wanted a 4 gigahertz signal source way back, you couldn't get transistors that would work at those frequencies, but you could get a voltage variable capacitor. So basically, they took a voltage variable capacitor made with a specially processed diode, mounted on a big chip that was heat sinkable, and they would drive that with a sine wave, and the capacitance changing across sine wave would generate harmonics, and the harmonics were taken out with tune circuits. And capacitor being a very low device, you could probably get 60% multiplication. So you put in 500 megahertz, you get out 1500 megahertz, and you get 60% of the power by using a voltage variable capacitor. And those have totally fallen by the wayside for any practical application, I believe, because they get semiconductors that work directly as amplifiers and multipliers at such high frequencies. Next.
Okay, Don, you just you left when as soon as he started your variac question, but I hope you got it all. Let's see, from Wendy.
I heard the whole thing. I was just walking around my computer.
Oh, great. Okay. Wendy, excellent presentation information. Bill Miller. Yes, excellent, Bruce. As an ex-power supply engineer, I would say you nailed it. No real conspiracy there that I saw. Electrolytics just dry up and fail after 5 years or so. Peter East, brilliant talk, Bruce. Took me back a few years. Kim Hay, excellent talk. A lot of information. Thank you. Mike, I don't know what have means there, but got to finish this.
Okay, so now everybody is real suspicious of their computer motherboard and computer power supply. And I don't know, I'll go for the conspiracy thing with the manufacturers. It always sounds good having a good conspiracy theory. So be suspicious of your computer. If it starts acting up, pull the cover off, look and see if half of the capacitors on the motherboard have a little bulge in the top. Well, that motherboard's pretty well toast. Especially the way they surface mount the capacitors now by robotics. You're not going to change them by hand easily.
Right.